This video doesn't create any radical new behaviors. There are no new script files here. We are just going to update some of the existing ones so that our objects look in the direction they're moving. So the player, both enemies, are going to face the direction we're moving them in. And it's actually built on top of some of your trigonometry knowledge. So hopefully you remember SOHCAHTOA. That's your handy mnemonic for remembering sine, cosine and tangent and their combination of sides of a triangle. The one in question here is the tangent. So the tangent works with the opposite and the adjacent sides of a triangle, which handily enough in a 2D game turn into the x and the y, which is perfect because every object in a 2D game moves in the x and in the y, even when they're moving diagonally, and that's how we get these triangles in our game. Obviously we're not displaying them on the screen in the game, but they're behind the scenes, they're the logic we're using to figure out this angle. Okay, so we know that the tangent of the angle is the opposite length divided by the adjacent length, or the y length divided by the x length. And we can take that, so that gives us the tangent of the angle. We can use a bit of code to reverse engineer that tangent to give us the actual angle. So we don't want the tangent of the angle, we want the angle itself, which means we're going to use the inverse tangent. And you don't have to worry too much about how you do that. The code's going to handle it for us, but that's the process. We figure out, or we know the tangent, and we can reverse engineer it to just get back to the normal angle. So I'm going to jump straight into code, and I'm actually going to start with the player controller, because it's the easiest one to do, because we've already figured out the triangle itself. We've done a lot of the hard work here. In this line, we create a vector that stores the direction that we want to move. It's also the direction we want to look, so we already have access to the x and the y of our triangle. So I'm going to make a new line in this function, and I'm going to store a floating point number called angle. And this angle is going to be calculated by using mathf, which is a class that handles all sorts of floating point maths, dot, and then start typing atan, and you'll see there's two options. So the atan is the arc tangent, so it's the inverse tangent. It reverse engineers the tangent to give us the actual raw angle. And there are two options. We can use atan, which actually requires us to pass in the tangent, and we've never figured that out, and we're not really going to, we're not bothered about it. We're going to use atan2, which actually lets us just put in the y and the x, and it will do all the rest of the work to give us an angle in radians, which is worth remembering because radians are not the same as degrees. We will need to do a little bit of work afterwards, but most of the work is done. So we pass in the y, we pass in the x, we've already figured them out because we've got the direction vector, and that gives us the angle in radians. So we're going to use atan2, and then in brackets it's going to prompt us for the y, so this is direction.y, comma, direction.x. They are done in that order for a reason, and it makes perfect logical sense when you remember that the tangent is the y over the x, so it's the y first. Okay, so that figures out the angle, but it figures out the angle in radians. The next step is to apply that angle. So I'm going to do transform.rotation, and that will let us set that rotation. So equals, and all rotation information in Unity is stored in a quaternion. Quaternions are a weird combination of maths that we want to try to avoid. So we're going to type quaternion, do a dot, and then we're going to use this Euler function, which lets us convert the angle back into something a bit more manageable that we recognize, an x rotation, a y rotation, and a z rotation. So we're going to choose that one. And then in brackets, because we're in a 2D game, we're not interested in rotating around the x-axis, so we're going to go 0. We're not interested in rotating around the y-axis, so we're going to put 0. And then we do want to rotate around the z. All rotation in a 2D game should be around that z-axis. So we're going to put angle. It's not quite perfect yet. I'm going to save it and just show you. So my player now should do a bit of rotation when I move. It's probably hard to tell in the video, but they are rotating ever so slightly. But because the angle that they're using is stored in radians, it's just plain wrong. So what we need to do is convert this angle to degrees. And luckily, Unity gives us a handy function inside the, well, not even a function, a handy number that we can multiply this angle by in the mathf class again. So mathf.rad2deg is a very handy number because we can multiply our angle by that number to turn it from radians into degrees, and that completes the line. So that line will now set our rotation to be our angle converted to degrees. Save it up, go back to Unity, let it compile and give it a try. And you can see now that the player faces where they're going. The only downside is if I let go of everything, they will snap back to face to the right. And that's just because when you're not moving, you're facing 0 degrees, which is by default to the right. There are ways to fix that. It's not game breaking though, so I'm not going to use video time on it. Okay, so there's our foundation. I'm going to copy these 2 lines because they are the main bulk of the maths. I'm going to copy them and I'm going to jump to the next one. So simple enemy movement is next up on the hit list. And we're going to apply the logic in a very similar place. We're going to find this move towards target function. Don't necessarily have to do it there. We could do it in update. We could make a new rotate function for it if we wanted to. Just find somewhere where it makes logical sense. And I'm going to paste those 2 lines in. And we hit a problem straight away. See how direction is red? Because we don't have a direction variable. We've never figured out the actual direction we're moving in inside of this class. We just tell Unity to do a lot of it for us. We use this move towards position. So we're going to need an interim variable. So above that float angle, let's make a vector 3 just to keep it consistent with the start point and the end point. Let's make a vector 3 and call it direction so that we don't need to edit any of the other code. And that is going to be our end point minus our current position, because that's going to give us the difference of where we are to where we want to be. Let's just see if talking over a picture of a triangle helps at all. If we're there and we want to look there, we just need the difference between these 2 positions. And the maths is very similar to if you've got a 6 and a 4 and you want to know the difference, you just take the 4 away from the 6. So if we're at 4 and we want to be at 6, the difference is just the 6 take away the 4. It's just that we've scaled it up to vectors instead. The actual logical order of it is exactly the same. So to find the difference, we want our end point minus our current position, and that will give us the difference between the 2, which is actually our direction. So that's perfect now. Save that up, go back to Unity, hit play, and you can see that the enemy, using the simple version of the movement, is now looking where they're going. And let's just snowball it from there. So I'm going to copy those 3 lines of code now because they've got an extra little bit to them. Copy them, going to jump to the complex enemy movement, and I'm going to work in the same function again, the movement function. I'm going to paste them in, and we've just got this one last remaining error because in the complex enemy movement we don't have an endpoint. The enemy doesn't move towards one set endpoint. It changes its mind and it moves towards the next waypoint instead, which is stored like that. It's waypoints index. So instead of endpoint, we're going to make it look at its current waypoint instead. Save it. The maths hasn't changed. We just needed a different triangle. Hit play. And now this enemy using complex waypoints will also look where it's going. What a game. It's just so good. Yep. Okay, the next step is the trickiest bit. We need to get the line of sight working. So I will see you in that one.